10.5, we're going to be looking at the polar form of complex numbers. And so just like when we learned about our polar grid, we're going to learn about our complex grid with this one. So the first thing I want to look at is plotting complex numbers in the complex plane. So when you're plotting, it's very similar to plotting real numbers, except your horizontal axis represents the real part of the number, the A part, and the vertical axis is going to represent the imaginary part. And so I'm going to kind of move down here and then I'll move back up. So this will be what your complex plane is going to look like. So you can see again, here's your real, so that would be your A, and here's your imaginary, so that would be your B value. And so it gives you kind of some how-to to work with it. It says, given a complex number, A plus BI, plot it in a complex plane. So first you're going to label the horizontal axis as the real axis, and the vertical axis is the imaginary axis. And then we're going to plot the point by moving A units horizontally and B units vertically. So to get us going, here's kind of an example, and so I plot it for us. You're going to plot the number 2, -3. So here's your A value, and here's your B value. So you can notice that we went over +2 and down -3, and here's our complex number. So it's not very bad to it's not very difficult to plot. You just kind of got to get your axis correctly, but very similar to what you're doing with your ordered pairs in your coordinate plane. Next thing that we're going to do is we're going to look at finding some information about where that is directionally. So for part 2, we're going to be looking at finding the absolute value of a complex number. So we're going to look at something called magnitude, so kind of some vocabulary to get us going. They say the magnitude of z, and you'll notice that it's the absolute value of z. You measure the distance from the origin to a point in the plane. And so really a picture helps us to see this. So the distance from the origin to the point in the plane is known as the magnitude, or the absolute value of z. And as you can imagine, notice if I were to drop an anchor here and create this triangle, that's essentially the hypotenuse of a triangle. So it makes sense that the absolute value of a complex number is, notice, that's just a form of the Pythagorean theorem. Your leg squared plus your leg squared, add it together, square root it. So still relating back to triangles, still relating back to directions, kind of like we were doing with our radii when we're in the polar grid. And so if we have a complex number, x plus yi, so they are switching to x's and y's to make it more familiar instead of your a and your b. The absolute value of z is defined as, and here it is, and it's the distance from the origin to the point x comma y. Notice that the absolute value of a real number gives the distance from 0, while the absolute value of a complex number gives the distance from the origin. So I just want to kind of talk about this, pick up some vocabulary, but let's definitely look with how we can use this in some problems. So I've got 2 examples for us here. So it says find the absolute value of z equal to the square root of 5 minus I. So now we're using x's and y. So you can see my x value is going to be the square root of 5. My y value is going to be -1. And so I'm going to use my formula here, and I say the absolute value of z is equal to the square root of x squared plus y squared. Start plugging this in. Square root of 5 squared plus -1 squared. So this gives me 5 plus 1, or the square root of 6. And so graphically, if you're thinking about this, I would have to go over, let's see. So the square root of 5 is about 2-ish, and then down that -1. So here's the point, square root of 5 minus I. So it would be this distance here from the origin to that point. And that value would be equal to the square root of 6. And so using the formula, it's not very bad. Let's do this other example here, maybe one without a square root. But again, the same thing is true. So this would be your x, this would be your y. So I would say z is equal to the square root of 3 squared plus -4 squared. Just working out our arithmetic here. And we can see that the absolute value of z in this case would just be equal to 5. Again, graphically, so we're at 1, 2, 3, 1, 2, 3, 4. So here's my point, 3 minus 4i. So this distance would be 5, or the magnitude of it would be 5. So I'm going into part 3. Now that we know how to graph the complex numbers and how we know now we know how to work with the magnitude of these complex numbers. Let's take it a step further and let's take our complex numbers and write them in polar form. So we get some formulas to get us going, and we're writing our complex number in polar form. So again, we're going to do x equals r cosine theta, y equals r sine theta. There's our r value there, similar to our magnitude of z. And then we're going to make some direct substitutions. So if we take what we already know and plug them into our complex number, we already have a substitution for x, and we already have a substitution for y. So I'm going to plug those in, factor out the r, and I now have my complex number written in polar form, where r is the modulus and theta is the argument, and then we also use the abbreviation RCIS theta to represent this form. So there is a shorthand for it, and this is the shorthand we will be using for it. So let's work a couple examples, and we're going to be using this information here, going from our complex number into our polar coordinates. Now it says express the complex number for I using polar coordinates. You'll notice that we typically have it in the form a plus bi or x plus yi. So in this case, my y value would be 4 and my x value would be 0. I do not have a real part to this. So the first thing that I'm going to do is I'm going to find my r. You'll notice in this problem I'm going to need r's and thetas. So I'm going to say r is equal to the square root of x squared plus y squared, because I know x and y. So r is equal to the square root of 0 squared plus 4 squared. So I end up getting the square root of 16, which is 4. So now I have my r value. The next value I need to find is my theta. Well, let's consider this. If I come over here, and here's my reals, and here's my imaginary, and I were to graph this at 4i, it would be at 1, 2, 3, 4. Here would be 4i. So if I want to go, remember, your polar reflects your distance from your pole and the angle that got you there. So if I'm looking at this, and I do this angle here, this is my theta. Notice that angle is an angle we already know, and so that means theta would be equal to pi over 2. So I'm going to come over here, I'm going to say z equals, and I'm going to go ahead and use this form right here. So that would be r cosine theta plus I sine theta. So it gives me z equal to r, which is 4, cosine of pi over 2 plus I sine of pi over 2. Since pi over 2 is on my unit circle, I could do a little bit more if I like, but just to go ahead and finish this out and write my coordinate, it would be 4 comma pi over 2 would be my polar coordinate, or we could write it as z is equal to 4 cis pi over 2. And so you can see most of your work goes into finding your r and finding your theta, and then it's a matter of plugging in from there. Let's look at this last example. It says find the polar form. So here's your x, here's your y. First step, I'm going to find my r. R is equal to the square root of negative 4 squared plus 4 squared. So r is equal to 16 plus 16, square root of 32. Reduce that radical, and that gives you 4 square roots of 2. So I have my r. No big deal. Next, I want to do is I want to find my angle. Now what you can do is you can go back up here and you can manipulate this one here, and you could say, well, cosine theta is equal to x over r, just dividing both sides by r, and I'm going to use that to try and figure out this theta that I need. So I'm going to come down here and I'm going to say, okay, cosine theta is equal to x over r. So I say cosine theta is equal to my x, which is negative 4, over my r, which is 4 square roots of 2. So my 4's cancel. I get cosine theta equals negative 1 over square root of 2. We know this to be negative square root of 2 over 2. And we actually know that angle. That angle is equal to 3 pi over 4 using your unit circle. So if I write this out, this gives me z equal to 4 square roots of 2 cis 3 pi over 4. So we were able to take our complex number and turn it into a polar coordinate, and also use the shorthand that we've now gotten from this page. Moving forward, we go into part 4 here, and we're going to look at converting a complex number from polar to rectangular. So let's figure out what we know with this. So first of all, they said convert the polar form of the given complex number to rectangular form. So notice information that we can gather from this. It has given us, here's our r, it has given us cosine of an angle and sine of an angle. Now we could go back and start working with the backwards conversion with it from the previous page on that gray box, but I want you to consider this. We actually know what some of these values are. If you go to your unit circle and you go to cosine of pi over 6, that value is square root of 3 over 2. Plus I of sine of pi over 6, that value is 1/2 from your unit circle. If I distribute this, this gives me z equal to 12 divided by 2 is 6, so I get 6 square roots of 3. 12 divided by 2 is 6, so I get plus 6i. So this would be my complex number to rectangular form. So then I would be able to graph it using my reals on my horizontal axis and my imaginary on my vertical axis. This one is presented a little bit differently. Find the rectangular form of the complex number given that r is equal to 13 and tangent theta is equal to 5 over 12. So let's consider what we know about this information. Tangent theta is equal to 5 over 12. So this tells me that this is my y and this is my x. Then from there, I can figure out my r. So remember, r is equal to 13. You can see that squaring the 5, squaring the 12 helped me to get that. And so here's an example of maybe the triangle that exists with this one. And so if I take z equal to r cosine theta plus I sine theta, my r is 13, that was given. Since tangent was 5 over 12, using that information, I can figure out my triangle, and now I can tell you any trig function about it. So I can figure out cosine theta. So cosine would be SOHCAHTOA, so it would be your adjacent over hypotenuse, that would be 12 over 13, plus I sine of theta, that would be 5 over 13. Distribute, and this gives me z to be 12 plus 5i. So based off the information that they give you, maybe you can draw a triangle. Maybe you can use it with another formula to figure out what kind of information it's giving you and what can it tell you about this problem in order to use the correct formula. So in part 4, you can see that we can go from a complex number from polar to rectangular form. So as we start winding down this section, we are going to get up into these complex numbers in polar form and talk about their operations. We're going to be talking about products and quotients. We're going to touch on powers, and then we will not talk about the square roots within this section. So picking up some of these operations. What if we want to multiply some of this? So multiplying your complex numbers in polar form, or products of complex numbers in polar form. Say you're given two complex numbers in polar form. In order to multiply them together, you're going to multiply your r's, add your cosines, and add your sines. Or a more complex way of writing it is in our shorthand of multiply your r's and then add your thetas, cis in between. And so it says, notice that the product calls for multiplying the moduli and adding the angles. And so to find this, notice some information that we have with this one. So it says, I am going to, here's my z1 and here's my z2. So I'm going to work through this. So to do z1, z2, I'm going to use this formula here. So that means I would have 4 times 2 cosine of add the angles, add the angles. I can reduce this down. That gives me 8 cosine of 225 plus I sine of 225. If you want to consider this in radians, maybe that's more beneficial. That would be like 5 pi over 4, I sine of 5 pi over 4. And so this gives me 8. Go to your trig circle, negative square root of 2 over 2i, plus I, trig circle, negative square root of 2 over 2. Distribute it. And this ends up with negative 4 square roots of 2 plus negative 4 square roots of 2i. And this would be the product of these two.